All right, the integral test for convergence or divergence, whatever. On the bright side, this one will tell you if something converges or diverges. And basically the way we're going to do that is we're going to take this sigma notation and turn it into an integral and integrate the puppy and see what happens. So it'll actually end up being more straightforward than it looks based on this definition here. But the main thing is, I want to point this out, we're going to, this is a function of x, this has n's in it, so we're just going to switch n's to x's, that's no big deal. But you'll notice this infinity up here, that might be tickling some alarm bells in your mind like, hey, wait a minute, wasn't that a trap? Didn't I have like a test about that a month ago? And yeah, it's called an improper integral. So if you don't remember these and you want to look them up on this site and find the video about that, just to remind yourself, it's called improper integrals. And it's going to turn out that you're not allowed to plug infinity into things. So when you have a definite integral with infinity at the top, instead of that, you're going to replace that with b. So you'll end up with a limit, integral from 1 to b. But then you'll take the limit of that as b approaches infinity. That's improper integrals in a nutshell. To avoid, technically breaking the rules and plugging infinity into anything, we're just going to replace infinity with a b, and then take the limit as b approaches infinity. It's one of those mathematical little, workarounds. So technically we're not breaking the rules, but basically what's going to go on in these problems is we're going to take whatever the formula is for the terms, for the nth term, we're going to integrate it and then plug in infinity and see if we get infinity back or 0. So basically if we do this integral and we get a divergent integral, or basically infinity as our answer for the definite integral, then the thing diverges. If we get a constant or 0, then it converges. So pretty good times. All right, so as usual, we like to test the harmonic series because we know that one really well, and we know it diverges, and we know it pops up all the time. So why not prove one more time that it diverges? All right, so step number 1 for the integral test is we're going to sort of turn this into an integral. So what we're going to say is, you know what? If this converges or diverges, then the integral from 1 to infinity, and this is a 1 by the way, whether this started at n equals 1 or n equals 0 or n equals 3, whatever, you're still going to plug in a 1 right here, because it turns out the 1 doesn't really end up mattering anyway. If you put a 0 in there, you'll get in trouble sometimes with like undefined stuff, so I would just always drop in a 1. Then we're going to turn, anywhere we see an n, we'll put an x instead. So instead of 1 over n, we'll have 1 over x, and of course we need a dx. So at this point it's just a very straightforward looking integral, except of course, we've got that infinity up there, so that's why we got to invent a letter b that's going to approach infinity for us so that we can keep our hands clean. 1 over b, 1 over x, dx. Alright, so now this is the improper integral that we're actually going to execute on. So we'll take the limit, we'll just keep the limit as b approaches infinity out front. 1 over x dx integrates to ln of x, absolute value. And of course that's from 1 to b. We're going to plug in 1 and b. So at this point, now this is what's funny about improper integrals. We sort of did all this limit junk to avoid having to plug infinity into anything. And yet when we evaluate this thing right here, we're basically going to plug in infinity, right? Because how do you take the limit as b approaches infinity? You try plugging in infinity. So what's the ln of infinity? Well, it's infinity. It's smaller than infinity, but it's infinity. So when you plug in infinity, you get infinity, and then subtract, you plug in 1, and you get 0. But as usual, that doesn't really matter, right? As soon as you have infinity in your limits or your sum or whatever, you're hosed. So even if you get an integer here, having infinity in the problem already hosed us over, and this thing diverges, which is nice, right? Because that's what we expected, since this is, after all, the harmonic series, which we know diverges. All right, good stuff. Another integral test. Now, just as a side note, whenever you walk up to one of these problems, it's a good idea to just look at things and take a guess, like sort of educated guess, and try and figure out if you think that thing converges or diverges. Just ahead of time, take a guess, so that when you finish the problem, if you're pretty sure something was supposed to converge, but then you do the problem and it diverged, you want to have something to sort of double check yourself against. So the reason I bring this up is because this thing to me kind of looks like it's probably going to converge. because I recall that the geometric series 1 over e to the n converges, and this is e to the n squared, so it looks like it would converge even faster than this geometric series. So that's why I'm guessing. It looks like these terms are going to be smaller than this geometric series, but hey. All right, so let's just go ahead and plug in to the formula. So I'm going to turn this into an integral from 1 to infinity of x over e to the x squared dx. And naturally, since that's infinity, I got to replace that with b and put a limit as b approaches infinity out front. A lot of teachers are total sticklers, and sometimes I hear on the phone from people using my videos to take math classes at college, and they have the worst teacher ever. Like, people call me to tell me that when I refer to bad teachers, their teacher is actually worse than that. So I know they're out there. A lot of people have real stickler teachers, and they will require you to write limit as b approaches infinity and b on absolutely every step, and take away points or give you 0 points if you don't do that. Those teachers are meanies, but they're out there, so I would just go ahead and do it, because why not? It's just a little bit of extra writing. All right, so if I want to integrate this puppy, now I'm faced with the task of integrating it, and the question is how to integrate this thing. I think we should rewrite it as e to the negative x squared. Yeah, it's just e to the x squared downstairs, the same as e to the negative x squared upstairs, x dx. And now if you rewrite it this way, you're like, oh, this is just an exponential integration. My u equals negative x squared, because that's the exponent of e. So my du is going to be negative 2x dx. And look at that, I've got an x. So I just need a negative 2, which means I need a negative 1/2 out front to make up for it. So at this point, still got my limit as b approaches infinity for all my steps. So e to the u du is just going to integrate to e to the u. So I got my negative 1/2 out front, and then I've got e to the negative x squared from 1 to b. Sorry about my bad writing. Negative 1/2. And then I'm just going to bring that e to the negative x squared downstairs. So 2e to the x squared from 1 to b. All right, so at this point, I can basically plug in infinity and see what happens. So when I plug in a really giant number, like infinity, to e to the x squared, I get e to the infinity, which is infinity. Negative 1 over infinity is 0. And then subtract, and then let's see. So then for when you plug in 1, you'll get negative 1 over 2 times e to the 1, which is just e. And those negative cancels. So this converges to 1 over 2e. Now, is that actually the sum of the series? Might not be. All we care about, and all this test, all the integral test tells us, is that if we get a number other than infinity, that this thing converges. So because this integral converged to 1 over 2e, which is a finite number, the original sequence or series converges. But again, this is not necessarily the sum of the series. All the integral tells you is that it also converges. All right, more integral test. What a shock. So let's see, we're going to go from 1 to infinity. Or better yet, let's just make that a b. Save ourselves a step. So I got 1 over x square root of ln of x. And of course dx. All right, so how are we going to integrate this thing? Well, doesn't it look like, the question is, what's my u here? And I think we've got 1 over x. And then if you rewrite this as ln of x to the negative 1/2, negative 1/2, you can see it as the power rule. So my u is going to equal ln of x. And therefore my du would be 1 over x dx. And oh, look at that. I've got a 1 over x and I've got a dx. So I don't even need to do any tricks here or add any constants. I can just integrate this to u to the 1/2. So there's going to be a limit as b approaches infinity of u, which is ln x. And now my new power is positive 1/2. And I divide by the new power, which is 1/2, so which means multiplying by 2. All right, and we evaluate this one from 1 to b, and of course b is approaching infinity. So now my usual final step, I'm basically going to plug in infinity for x and see if it's infinity or if it's a reasonable number. Natural log of infinity is infinity. Square root of infinity, still infinity. So I get 2 times infinity, which is still infinity. And it doesn't even matter what this other one is. I mean, it's probably 0, but point is infinity, so this thing diverges. So again, because the integral diverged, gave me an answer of infinity, that means that the original series also diverges. That's the integral test. So you can see how these might get a little dicey. If they were mean, they might give you something like, integration by parts or trig sub. Most teachers won't do that, but you can see that possibility certainly is out there. And oh, look at that. This might be one of those. So once again, they're saying use the integral test. And by the way, if you need to use the integral test, they'll usually tell you to use it because there's better tests out there. Other tests we'll look at will be just as effective and usually easier. So the only time you'll usually use the integral test is when they tell you to use the integral test, or if you're on the AP exam or something, or have sort of more like theoretical teacher in college, they might ask you something sort of like theoretical that involves the integral test formulas or theorem. But the moral of the story is, if they say use the integral test, you should use it. Otherwise, you're probably going to use something easier. All right, so this one happens to be, even though it looks funky, it is integratable. So we got x over x to the 4th plus 1. And I think this is actually an arctangent, because for arctan, the formula is u squared plus a squared. Downstairs, it's like du over u squared plus a squared. So if our u was x squared, then x to the 4th would be u squared, and our du would be 2x. So that means I just need a 2 here, and therefore a 1/2 out front. All right, so I get 1/2 times ln, limit. So 1 to b of du over u squared plus 1. All right, so this is going to integrate to 1/2 times arctan of x squared. And of course, it's the limit of that. This b approaches infinity from 1 to b. All right, so this one, it might not be obvious, but this actually, you have to be careful, because even though it looks like we're plugging in infinity, tangent goes to infinity sometimes. So we got to be super careful when we plug in here. So the question is, what is the arctangent of infinity? It's actually pi over 2, because the tangent of pi over 2, or 90 degrees, is infinity. So we've got 1/2. So we plug in infinity, we get pi over 2. And then, for when we plug in 1, we've got 1/2 times, what's the arctangent of 1? 1 squared is 1, and the angle that has 1 as its tangent is pi over 4. So kind of crazy, right? Even though we plugged in infinity, we got a reasonable number. We got pi over 4 minus pi over 8. Now again, and this ends up equaling just pi over 8. But this number doesn't matter. The actual value, pi over 8, does not matter. That's not what the sum is equal to. That just, because we got a finite number, a constant, that means that this series converges. If we had gotten infinity, it would have diverged, but we got a finite number, or 0, which means it converges. All right, tricky one. I know it's tricky because it says tricky. It looks pretty straightforward though, doesn't it? So let's see why it's tricky. Limit as b approaches infinity. What could go wrong? X over x plus 5. Oh, I see what's tricky. we're going to have a really tough time matching up our u and our du. You'd be tempted to do a natural log integral, but that would make your u x plus 5, which means your du would not have an x in it. That x is extraneous. So it turns out that if you want to integrate this one, you would have to do partial fractions. Or actually, I think you'd have to do long division first. So you'd have to do x plus 5 into x. And, and then that's how you get your partial fractions. Actually, don't do partial fractions, I guess. X plus 5 into that is just 1. X plus 5, negative 5. X into that, so that's our remainder. So negative 5 over x plus 5. Okay, so it turns out that if you integrate this, so this integral becomes the integral from 1 to b of 1 minus 5 over x plus 5. All right, so you could take it from there. It'd just be a natural log. But here's the thing. We don't actually have to do this. And this is why we want to keep an eye out. Even though the integral test is one of the more difficult techniques, sometimes they'll throw in a trick problem where you don't need the integral test. What type of series is this? Is it one of the ones we've already talked about? Is it a p series? Is it a geometric series? What it is a divergent series. Because remember, the very first test we learned is the nth term test. So basically what that says is that the terms have to be approaching 0. As n gets bigger and bigger, as we get to like the 100th term, the 1000th term, our terms need to be approaching 0 in order for the series to converge, for the sum to be a finite number. And this doesn't do that. The limit, as n approaches infinity, of n over n plus 5 is just 1. And you can see that by using L'Hopital's, where we take the derivative of the top and bottom. We just get 1 over 1. Or you could just see it from sort of a logical standpoint, that if you plug in 1,000, you get 1,000 over 1,005, which is pretty close to 1. Plug in 1,000,000, get 1,000,000 over 1,000,005. So basically, the bigger n gets, the less this 5 matters. And so basically the limit is just n over n, which is 1. Anyway, point is, if you've got an easy out and you can see right away that it diverges, that's a good way to go. So that's another reason to sort of take a look at the formula and try and guess what the answer would be before actually executing one of your ratio tests or your integral test or something. Because sometimes it'll be a simple question in disguise, and you can just spot right away that it diverges. Or converges. Might be, maybe you're in the integral test chapter, but then they gave you one you can use the p-series test on because it's really obvious that p is 2 or 3 or something. So just keep an eye out for the simpler ones. All right, and lastly, here's another integral test. Why is it hidden? Well, it's not that hidden. It's just that this thing looks pretty hard to integrate. Because usually if I want to integrate a big fraction like this, it might be a little bit hard to get your du and your u to match. So you might be sitting here thinking like, oh my gosh, I've got to use partial fractions or something crazy. But this thing, actually, we can factor the bottom into being x squared plus 1 squared. So now it's just a basic power rule. And once you see this, it'll turn out that it converges. So you can see right away we have the bottom is pretty big, so this is kind of like a p-series in disguise. But alternatively, we can just integrate it, so we'll get your u equals x squared plus 1. So your du is just 2x dx, which is, oh, look at that. That's right there. So this just integrates to being the limit as b approaches infinity of negative 1 over x squared plus 1 to the first power. And of course, when you go from 1 to b, plug in infinity to this puppy, and you got 0. And then minus a negative 1/2. So again, 1/2 is not the actual sum of the series. Just the fact that this is a constant, it's not infinity, means that the series converges. So that's the integral test. Again, you probably won't use it unless they ask you to. Stick around for stuff you will actually use more commonly.